Hi, welcome to this video on the mass spectrometer. The aim of the mass spectrometer is to measure the mass of different substances. Okay, so in this case we may want to measure the mass of elements, molecules, things like this. So we're going to determine their relative molecular mass. It all starts in this process here where we've got a sample, something we want to investigate. We want to find out the relative molecular mass of this sample. What we're going to do is it's going to be injected into this first area of the mass spectrometer, and in here it is going to evaporate and become vaporized. Okay, so it is a vapor, and that means essentially it's a gas. And this vapor, this gaseous sample, is now going to go through the process of going through the mass spectrometer, and in that process we'll be able to determine its mass. So how does that happen? Well, the first step is called ionization. Now, ionization can happen in two ways. One, we can use a thing called electron impact. And two, we can use a technique called Electrospray ionization. Now I'll talk about those two in detail later on. But essentially what's going to happen is in this sample we are going to create positive ions. Okay, and obviously these are not to scale, but we're going to create gaseous positive ions. And that allows us to move on to the next stage, which is called acceleration. So stage 2 up here is called acceleration. And acceleration takes advantage of the idea that we've made all these positive ions. Because what we have is we have a metal plate. Here's my metal plate here, and it's got a hole in the middle of it. And the metal plate is negatively charged. Okay, so we've got a negatively charged metal plate. Technically, the number is minus 5,000. Okay, it's minus 5,000 volts. But as long as you know it's negatively charged, you'll be fine. And what we do is these positive ions here are attracted to the plate. And when they hit the plate, they discharge. But this one here, when it gets attracted, it's going to slingshot through and go through the hole. Now the most important thing to remember about the negatively charged plate is it's going to mean that all of the ions that go through this hole have a constant kinetic energy. Okay, and that's really, really key to remember. Every ion that travels through this hole has the same kinetic energy because they've all been influenced by a negatively charged plate, which has a minus 5,000 volts, and they're all a plus 1 charge ion, and so those two things mean that we're going to have a constant kinetic energy. Now, when they get through this hole, they end up in a vacuum. And this vacuum is here so that the ion can travel along this tube completely unimposed. It's not going to have any collisions, it's not going to be deflected by any stray ions there, it's completely empty. And this tube could be a meter or so long, and what's going to happen is these ions are going to drift. So we have ion drift, and here's our positively charged ion, and it's drifting. Okay? Now, this allows us to separate out the ions, because if we remember our kinetic energy equation, Ke equals half mv squared, and we realize that the kinetic energy for each thing is constant, then essentially what it's going to tell us is that as the mass goes up, the velocity is going to go down. Now, we won't get into the inverse square relationship right now. We just need to know that heavier ions will travel slower through this drift. when they travel through this ion drift stage, this third stage, eventually they meet a metal plate at the end. And this metal plate is known as the detector. So our final stage is detection, stage 4. What happens is our ion is here, it hits the metal plate. The metal plate is full of delocalized electrons, and these electrons discharge the ions when they hit. When those ions move, it causes a current to flow. Our sensing equipment in the computer can detect that current, and it can determine the abundance of each ion. So they know which one is more common, and they know how big it is. And then the computer does some analysis and determines and gives ourselves a mass spectrogram for us, or mass spectrograph for us to look at, and that allows us to determine a few things. So overall, to summarize, the mass spectrometer has 4 stages. Ionization, where gaseous atoms turn into gaseous ions. Acceleration, where a negatively charged plate accelerates the ions to a constant kinetic energy. Ion drift, where they drift through a vacuum tube and the smaller ions travel faster. And then when they hit the plate at the end, detection, where a current flows and the abundance of each ion can be determined. That's how the mass spectrometer works. What we're going to do now is we're going to look at electron impact and electrospray ionization, so the 2 methods for this first stage, in a bit more detail. So let's start off with electron impact. This is the most straightforward one. What we're going to have is we're going to get out our trusty electron gun. Now the electron gun essentially creates a beam of electrons. So here's my electron, and those beams of electrons are going to be fired through the gaseous sample, and what they're going to do is they're going to strike the outer electron of an atom and ricochet off, a bit like the cue ball in snooker or pool ricocheting against the red maybe. As that happens, the electron will be jettisoned into space, okay? In this case, the space of the chamber, not outer space. And this creates an overall electron deficit, and that is our positive gaseous ion. Now this process is often done with low relative molecular mass samples. So we're talking about elements, diatomic molecules, inorganic things like that, okay, small MRs. And what we have is we have a +1 ion formed no matter what we've got. So let's say we took lithium. The lithium would be a gas. It would undergo the impact and it would become a +1 ion that's still a gas, and the electron would remain. But if I took bromine, now bromine exists as a liquid at room temperature, but in our mass spectrometer it's going to be a gas. And it exists as diatomic molecules. When we form our positive gaseous ion, it's still going to be a diatomic molecule. It's going to be Br2 plus and an electron. Okay. If I was to choose something even stranger, it would still do the same thing. The whole thing would become a +1 ion. It's always gaseous, it's always +1. So for low MR things like elements, etc., we're going to use the electron impact, the electron gun, to create these positive ions. Now, the second way of doing it is electrospray ionization. And we use this when we've got a high relative molecular mass. Now, what does a high relative molecular mass mean? Well, what we're essentially saying is we're thinking mainly of kind of biological things. So proteins, pigments, things like that. Okay, we would use electrospray ionization. Now this triangle over here in my diagram is a hypodermic needle, and it's at a high pressure. And in it we have our sample, and we're going to call our sample M. Okay, so really it's super small. We're going to draw them bigger so that we can see them. So M is a really large biological molecule. And M is dissolved in what we call a volatile solvent. This needle, as the high pressure squirts the volatile solvent and these large molecules out of it, this needle is positively charged. And this is where we kind of get a little bit vague. So what we're going to say is, through this process, M, the large molecule, as the solvent that's volatile means it evaporates really easily, it leaves behind protons. And these protons stick to the large molecule, and you get this MH+. So we'll say this is a gas, and we'll say this is a gas as well. So in this area here, I've got MH+, MH+, and then this is my acceleration panel here. This is my negatively charged plate, and these will fly off through the accelerator into the drift stage. So electrospray ionization, our molecule is dissolved in a volatile solvent, which is pushed through a hypodermic needle at high pressure, which is positively charged. It then gains a proton or a H+ ion and forms NH+ that's a gas, which can then be accelerated. That's how we would write that kind of answer. So we've gone through two methods of ionizing here. Now, I've got a little bit of practice for you here for what we've talked about so far. What I want you to do is pause the video, and I want you to have a go at each of these 10 questions, then unpause when you're ready so we can go through the answers. Okay, good luck, off you go. Okay, let's look through some of the answers. So here are the answers for you to check. I won't go through lots of them. I will point out, first of all, that electrospray, you have to gain a proton. Please remember that. Okay. And I will say that this bottom one, 10, you could have different answers. You could, for example, say that when the ions enter the drifting tube, they have different velocities. You could say have the same charge, maybe. They'd both be true, but this is the one I want you to remember. We have a constant kinetic energy. So I'll pause for a second to give you a chance to read through them and mark them off. And then we're going to talk about what the mass spectrogram looks like and how we can determine a different piece of information from the spectrograph that we see. So here we have a very, very simple mass spectrograph, just so I can show you what it means. For the record, this is for the element boron. Now at the bottom here, we've got a thing called the MZ value, and the MZ value stands for the mass divided by the charge. Again, the reason we divide by the charge is because although most ions are +1, every once in a while we get a +2 ion, and this equation, by dividing by the charge, it prevents it from interfering with the main peaks. It moves out the way, and so we don't accidentally interpret it as being kind of half the mass that we're supposed to. We can see it out the way. So when you're asked about why it's mass divided by charge, we really want to answer that we're accounting for the accidental creation of 2+ ions. And they happen very infrequently, but it's worth noting that they do. Now in this case, we're doing a mass spectrograph of a single element. In this case it's boron, and you can see we have two isotopes. We have boron 11 and we have boron 10. And we can see there's two isotopes because we've got two bars. And we can also see that 11 is more common than 10. Now on the side here you've got a thing called the relative intensity, or it can measure a thing called the abundance. In the case of the intensity, it's a percentage, with 100 being the height of the biggest isotope. Not the biggest is the wrong word, sorry. We should say the most abundant isotope, because it's not about whether it's 10 or 11, it's about which one has the highest bar. And in this sample of boron, we essentially have 80% boron 11 and 20% boron 10 in the sample, because 100% here is our 80% and 25% is our 20%, because it's in fifths. So we've got 4/5 of 11 and 1/5 of 10. So when we're looking at monoatomic mass spectrographs, they're really simple, really easy to read. Okay. Sometimes we hear the language of the molecular ion peak, and when you think about the molecular ion peak, you want to kind of think of the biggest one to the right hand side. In this case we'd say 11 was that, but often it's referring to more complex molecules than these monoatomic ones and diatomic ones. It's talking more about small organic molecules, maybe, things like that. Now over here I've got the spectrum of bromine. If we look at this carefully, first of all we can see it's still got MZ underneath, and it's got relative intensity at the top. It has over here two small peaks. These two small peaks are for when the Br2 molecule gets hit by the electron and accidentally breaks up into a gaseous atom and a gaseous ion. Again, it doesn't happen very often, which is why they're so small. But if you look at these two numbers, if I zoom in a little bit, you can see that one is at 79 and one is at 81, which are the two types of isotopes there are. These teeny tiny ones that are right down here, these are the doubly charged ions of the molecule. And so you can see how infrequently that happens. But it does happen. But they've been taken into account. They're down there on the mass spectrograph. We're more interested in this side over here. So on this side we've got a big peak at 160, and then we've got kind of relatively two peaks that are kind of relatively equal in intensity, and one of them is at 158 and one of them is at 162. So why do these peaks happen? Well, bromine is a diatomic molecule, Br bonded to Br. Now bromine can exist as a 79 or an 81, and they're relatively equal. I think it's kind of 49-51, but we can assume it's essentially 50-50. So there are four possible outcomes of our bromine that can occur. Here we go, here are my four possible outcomes of my bromine. I've got 79 and 81. I could also have 81 and 79. I could also have 81 and 81. I could also have 79 and 79. And when I do the maths, I see that these two add together, let's do that neater. These two add together to make 160. This one equals the 162, and this one equals the 158. So by looking at my mass spectrum of bromine, I can not only tell the proportions of each isotope, but I can also see how they're bonded and how that affects it. And because this is twice as likely as these two, you have essentially one bar in the middle here that is twice as high as the other two bars. So over here I've got some questions for you. Okay, these questions talk about how to work out the relative atomic mass from percentages and how to draw a mass spectrum. If you just pause it for a second, have a go at the questions, then unpause it, and we'll talk about the answers in just a second. Good luck. Okay, so here's the answers. Again, I'll just pause for a second and let you have a look at it. Make sure you've got your workings correct. Excellent. Well done. So some of the things that overlap with this topic are the requirement for higher tier maths questions. And one of the areas they like to work with is using these two formulas, the kinetic energy equation and the velocity equals distance divided by time question. And these are two versions that they often give you. And they like you to use these two equations to determine different things. So one thing they like you to determine is the length of the tube. So here's our drift tube, and we know that ions are entering it with a +1 charge, and we know that they all have the same kinetic energy, okay, or EK. And then if they give us the time and they tell us that, then we can work out this distance of the tube. That's the kind of question they can ask us to do. So here we've got an example where we've got an element Q, which could be any element, and it's been ionized in the time of flight mass spectrometer, and it's got a kinetic energy of 8 × 10⁻16. The time of flight of 82 Q+, so they've told us the relative atomic mass there of 82 is 1.283 × 10⁻5 seconds. And the mass of it is this, and they've given these numbers to us. We will not be able to know these numbers, we're not expected to figure them out. It's just asking us to calculate the drift tube. Now there's a number of ways to attempt to attack these questions, but it's best in my opinion to go through it step by step. So first of all, we know that if we list our values, we've got an EK equal to 8 × 10⁻16. We've got a time equal to 1.243 × 10⁻5. We've got a mass of 1.369 × 10⁻25. That's a really small number, but it's kilograms, and atoms and ions are very, very small, so that should be perfectly fine. And we're after calculating distance, the drift tube. That's what we're trying to find out. Okay, and we know we've got our two equations. We've got EK equals half mv squared, and we've got velocity equals the distance divided by the time. So our strategy is going to be, if we can work out the velocity, then we can use the time and the velocity to work out the distance. So we need to work out the velocity using the first equation. So if EK equals half mv squared, that means 8.00 × 10⁻16 equals 0.5 times 1.369 × 10⁻25 times v squared. So now what I need to do is do some rearrangement. So I'm going to go 8.00 × 10⁻16 divided by 0.5 times 1.369 times 10 to the power of -25 equals v squared. Now if I want to get rid of a square, the opposite function is a root, so I can get rid of that, and I can put the whole thing in a big square root, and then I can use my calculator to make sure I get the right answer. And when I put this in the calculator and hit equals, I get a number that is 108,108. And it's essentially recurring, so it's 108,108 meters per second. So that's my velocity. If I know that, now I can work out my distance. Okay, so if velocity equals distance divided by time, then distance equals velocity times time. So my distance is going to equal 108,108 multiplied by our time, which is 1.243 times 10 to the -5. Get that number, times it by that number, and we get a distance of 1.3437 meters. so I'll probably round that up to 2 decimal places. I would think of 3 significant figures because I've got 8.00 there, so I'm going to go for 1.34 meters as my answer. Now there are other ways you could do it. You could put both expressions into each other and make one solution and just put all the numbers in on your calculator and get to it, but I prefer people doing it step by step so that if we find mistakes we can identify where we went wrong a lot easier. Now, time for you to have a go. Okay, pause the video here, make a note of the important factors. It's a very, very similar question to the one that I've just done. If you get stuck, rewind, rewatch the worked example and take it from there. Good luck, off you go. Now let's see if you've got an answer that agrees with me. So I'll zoom out a little bit. I got the answer of 1.499 meters, so I rounded that to 1.50 meters. Do you agree with my working? Although I've just noticed that needs a bracket. If you did, congratulations, well done. If you didn't, go back, have another go, see how you got on. Now we're going to move on to the next thing they can ask you to calculate. So now we're going to be asked to calculate the drift time, the time it takes it to drift through. We're going to use exactly the same two formulas. We're always going to use them. Sometimes in questions they may give you them partially rearranged and things like that, but I'm just keeping to these two that are the same because they're the standard format. And in my example here, we've got Q again. We've got a standard kinetic energy of 8 times 10 to the minus 16 still, but we're told that the tube is 1.8 meters long. Now we're going to assume this question is completely independent from the question before, so that we don't need to use a ratio way of solving these problems or anything like that. We'll be following a very simple methodology that's exactly the same as before. Okay, we're going to calculate the time taken. So now we have the kinetic energy, we have the distance now, we have the mass, we have all these things, but we need to find the time. So if we know that EK equals half mv squared, then what we're going to do is we're going to find V again, and we're going to put V into V equals distance divided by time, but this time we're going to find time instead of distance. So it follows a very similar process. So 8.00 times 10 to the minus 16 equals 0.5 times 1.369 times 10 to the minus 25 times V squared. Now you'll notice these numbers are similar to the ones we used before, so we should be able to solve for V squared doing exactly the same thing. We're going to go 8.00 times 10 to the minus 16 divided by 0.5 times 1.369 times 10 to the minus 25, and we're going to square root that, and that's going to give us V, and that's going to give us a value that is exactly the same. So our value is going to be 108 meters per second. It's the same ion being involved, and it's got the same kinetic energy, so its velocity is exactly the same. But now we're just going to do V equals D divided by T, so T equals D divided by V, which is 1.8 divided by this 108, and we're expecting a very small number here. So 1.8 divided by velocity equals 1.665 times 10 to the minus 5 seconds. So we'd probably round that to 1.67 times 10 to the minus 5 seconds. So that's how we do it. Now it's time for you to have a go. So again, similar type of question, but you've got a slightly different scenario, different length of tube, different mass. Off you go. Good luck. So let's have a look at the answer. So what we've got here, I'll zoom out a little bit, is our answer to that question. Exactly the same workings. You're getting a different velocity. You're getting 105,555.96 meters per second, and that gives you a time of 8.53 times 10 to the minus 6 seconds. A very short time, but these things are traveling very, very fast and they're very, very small. So that's to be expected. Excellent. How did you go? Well done. Now, we're going to do our final bit of calculation now, which is a little bit of ratios involved. So the final way they can ask you some more tricky maths involving this topic is by giving you information about one ion's time and asking you to find the time it takes the other isotope to travel the same tube. So we're still going to use the same two equations. I've got an example over here. Let me zoom out a little bit. So here I've used a Br plus ion. Now you'll remember from the beginning of the video that generally these things would be diatomic molecules that are ionized. I've chosen this as a very simplified example just to show you how to do it. Okay, but we've got 81 and 79, and so this one's the heavier one, and that's how long it's taking. Okay, and it's flying across the same mass spectrometer. How long would it take a 79 ion to travel down the same flight tube? So we've got a tube like this, and the 81 bromide ion is traveling down in a time of 2.63 seconds times 10 to the minus 5 seconds, sorry. Okay, and we'll call that T1. And then you've got the 79 isotope, Br plus, that's traveling down, and we'll call that T2. Okay, and we don't know what that is. So we're going to use our formulas like before. We're going to use EK equals half mv squared and velocity equals distance divided by time. But in this case we need to put the distance divided by time into this equation. So we're going to have EK equals half m times distance divided by time squared. And if we want to, we can expand out those brackets and go half m times d squared over t squared, and that may be helpful for us. Now, we know that this is the same length. This tube is a constant length, and we know that EK is always the same. So we're going to use that to our advantage. What we're going to do is we're going to stipulate two versions of this equation. We're going to have the version for the 81 bromide ion, which we'll use red for, and the version for the 79, which we'll use green for. Actually, that's not very nice if you are colorblind. So let's say we are going to use blue for that one. Okay, so that one's going to be blue. So starting off on my red side, what I'm going to say is I've got half M1, which is the 81 ion, times D1 squared over T1 squared. And I've left it in this format because I'm going to cancel loads of things out. Don't worry. You could express it slightly differently with everything all over the top. That's up to you. And that equals half M2 D2 squared over T2 squared. And you'll notice there are lots of things here that are going to be constant that we're going to cancel out. So I'm going to cancel out the halves on both sides, don't need them. I'm going to cancel out the distances, don't need them because the distances are all the same. And I'm going to simplify this out, and it's going to look a little bit like this. It's going to look like M1 over T1 squared equals get my colours right, equals M2 over T2 squared. Now this is a ratio arrangement, so I don't need to use the actual masses in kilograms. I can just use the relative atomic masses. So So because this is a ratio of atoms, I don't need the actual mass, I can just use the AR. And if I've got the AR, then I can use that ratio between 79 and 81 to work out my time. So M1 is the is the 81, and I'm dividing that by T1 squared, which is 2.63 times 10 to the minus 5. 2.63 times 10 to the minus 5, and I'm squaring that. And that's going to equal M2, which is 79, divided by this second time that is squared. Now the easiest thing for me to do is solve 81 over 2.63 times 10 to the minus 5 squared first. Okay, so 81 divided by 2.63 times 10 to the minus 5. And then square that. And that gives me a number of 1.171 times 10 to the 11. And so now I know that 79 divided by T2 squared equals this number. So if I want to find out T2, I'll probably use the correct colour, that would help, wouldn't it? If I want to find out T2 squared, then I can go 79 divided by 1.171 times 10 to the minus times 10 to the 11, and if I want to find out T2, I can square root that number. Let's see what we get. Okay, so we've got 79 divided by 1.171 times 10 to the power of 11, and then we're going to square root that answer, and we get a time of 2.597 times 10 to the minus 5, and we're probably going to round that up, so 7 rounds to 0, 60, 2.60 times 10 to the minus 5 seconds. Now, does that answer make sense? Have I done this right? So I've got 2.60 times 10 to the minus 5. Add 2.63 times 10 to the minus 5. They're similar in mass, and this one's slightly shorter time, but we know that the lighter ones, the less mass, should travel faster, so that makes sense. So I'm happy that that is the correct answer. So if I zoom out a little bit so you can see the whole thing, we figured out what we needed to do and combined our equations. We then had equal sides and cancelled out all the constants that we had, and then we found and solved one side and used the ratio of the relative atomic masses to work that out, and then we finally solved for the second time. And then our last step was we checked that they were both relatively sensible answers. Here's a very similar question. Okay, pause the video, get a piece of paper, have a go and see if you can find out the right answer. Okay, good luck. Now, you've been working on this and hopefully you've got a time, okay? Hopefully your time is quite close to 1.83 times 10 to the minus 5 seconds. Let's see if you agree with me. Here's my working. Okay, again, pause the video and check. I followed the same method as before, and I came out with 1.78 times 10 to the minus 5. I wonder if you agree with me. Excellent. So this has been a long video all about the time of flight mass spectrometer. We've talked about how it works, how it's structured, the different stages. Yeah, so ionize, accelerate, drift, and detect. The different ways of ionizing, electron collision and electrospray ionization, how to interpret a mass spectrometer, and how to use higher tier maths content in exams to answer the more challenging questions that arise. If you found this video helpful, make sure you like and subscribe. I'm going to be trying to put out more content as the year goes on, and it would be great to have people's feedback. So please feel free to leave a suggestion in the comments. Okay, thanks for watching. Bye.